Okay, here we are. Welcome everybody, and thank you for being here today, and thank you, Mas, for giving me this possibility to introduce you these two outstanding case studies I modeled in Diana environment and FX Plus for Diana environment. I was performing these two case studies within the SAC Master at the University of Minho, and I was helped by my supervisor, Dr. Nuno Mendes, and my colleagues Jacopo Scacco and Gerardo Salazar. So the webinar will deal with the modeling procedure of two 3D solid models done in Diana and FX Plus for Diana, and all the modeling procedure from the geometry up to the results of advanced analysis, such as modal analysis, pushover analysis for the first case studies, that is Carmo Convent, and mainly dynamic analysis for the second case study, which is a Buddhist temple in Myanmar. And then we can go on with the results and the conclusion later on. Let's start with the first case studies, Carmo Convent. The Church of Carmo Convent is located in the center of Lisbon city, and it is one of the most visited attractions of Lisbon, and it was built at the end of the 14th century in a Gothic and Neo-Malin architectural style. As you can see from this picture, the church is very complex. It has 3 naves, 1 transept and 5 chapels. It is just the very traditional Latin cross plan of the Gothic churches, and as you can notice, it doesn't have a roof system. This is because it suffered many earthquakes during its history, and the most severe seismic actions occurred in 1531 and 1755. After the last major earthquake, locals decided to leave Carmo Convent as it is, damaged as it is, in order to make it to become as a symbol of this strong earthquake. As previous work, in order to understand the destruction, be aware of the complexity of the geometry, we performed a photogrammetry and many drawings in order to have a kind of plan where to start to model in Diana environment. And of course, it was also worth to have an idea of the damage along the structure and the evaluation of the masonry, which is mainly stone masonry, but the variety is significant because we can have large and big blocks, but also irregular and core material. In order to achieve some material properties or other more technical details, we had to perform non-destructive tests such as sonic tests, vibration tests, and dynamic tests. Talking about sonic tests, these are really useful to depict the linear material properties of the structure, these material properties will be implemented in Diana directly. Then vibration tests are useful just to have an idea if other actions, such as the metro line which runs below of the convent, can have some influences on the seismic behavior. And then dynamic tests, which are, I think, the most powerful tool to depict the dynamic behavior of the structure in terms of frequencies and more shapes. And then at the end, we perform also a comparison between the numerical results with the limited cinematic analysis and the empirical approach. But this part is out of our purposes in this webinar. So let's start going to the detail of the structure. As you can notice, the geometry is really complex, and therefore we need to simplify the geometry of Carmo Convent in a more appropriate and conscious way. I suggest you always to think about the the possibility to pass from the photogrammetry to the CAD environment and then in Diana environment. To do that, I suggest you to take into account that the edges and the geometry should avoid tiny and small parts in order to have a more easy meshing phase. And also, it's important to evaluate the connection between the walls, transversal and longitudinal. And for example, we noticed that this part of the convent was added later, and therefore there is the complete lack of cohesion between the elements. And because of that, we decided to discard this part from the 3D solid model. And so now we are going to start our process within the modeling procedure, thinking about the settings which are recommended in AutoCAD and Diana. First of all, I suggest you to set a high level of precision in length and angles, and possible the same. Be aware of the units and also where we are going to place all the surfaces, but also the solid that we are going to export in Diana environment. And for example, here I just imported the surface of the arch that later we will use to create some elements. How to export 2D surfaces from AutoCAD to in Diana? Okay, we have to create a region, and it's possible just to typing the command region from the toolbar or also from the graphical interface of CAD, and then we can export the surface in IGES file. Save the name of the file, and only later we can select the region we want to export. And then from Diana, it's very easy because under File, Import CAD File, we can select our IGS file we want to import. Okay, now it's not possible in just 1 hour to explain you all the procedure, how we made Carmo Convent, but I would like to go into detail of some particular geometrical portions, and let's start with arches and pillars. First of all, from this picture, you can notice that this element is composed by a basement, which is high 2 meters and 20 centimeters, and then the column, which is high 80 meters, and then the arch is settled at the total height of 10.2 meters. And so we are going to import in Diana exactly these surfaces, which contains the information of the basement, the information of the pillars, and also the information where the arch will be settled. So now we can start, and then we import, and we extrude the basement below in the Z direction. Okay, from the command extrude shapes, and then, okay, 2.2 meters in the Z direction, and then we move the line at the level of the arch, and then we can extrude also the pillars. Okay, then everything is ready, and we can add this sheet, making the half of the surfaces of the pillar, and in this way we can create the arch in a very fast way. Okay, let's finish this sheet. Okay, now we import the profile of the arch. It will be, I think, at the basement level. Okay, and we move the profile here at the middle of the surface, and then we do the command sweep. We will use a box to trim the final part below, and this phase is very useful to avoid tolerance problems or inconsistency in the geometry. And the final mesh will be easier. And then, okay, we have to repeat all the procedure for all the arches, paying attention, of course, on the connection between all the elements which compose the arcades of the naves and also of the transept. As you can see, now we can also create the vaults of the chapels. I'm showing you just how to create the biggest vault, which is the main element here. And as you can see, we did a kind of discretization of the shapes. Instead of having a rounded shape, we have a polyline made of segments. And okay, so we start from the profile of the vaults. We divide the arch in several segments, as already said, and we create the polyline following the boundaries of the edges, and then we can erase from AutoCAD the arch we utilized before. We join the polyline, and then we can do the offset of the thickness of the wall, which is set at 0.35 meters. Sorry. Then we cut. We just need half of the cross section of the vault, and then we can erase it. And we join the cross section, and we move the cross section at the lowest corner of the profile plan of our main vault. And then we move in the 3D view in order to rotate the cross section in Z direction. So view configuration list, front, and then we rotate. Okay. Should be here. Okay. Then it's possible to use a very powerful command, that is the command sweep, that is present also in CAD, not only in Diana, and we follow the path of the plan of the vault in order to create our solid. Okay, here we are. And then it's important to underline that before, for surfaces, we need to convert the surfaces in region. But for solid elements, this procedure is automatic. So we can just export the solid element in AutoCAD, in Diana, as IGS file. And then we repeat for all the other vaults. It's important to underline that for accommodate the vaults on the walls of the chapels, we need to create a kind of step to place properly the vault on the walls which is already existing in the model. And okay, so now we can talk about the material properties. As already said, we performed several sonic tests, direct and indirect, and along all the structure, all these points that you can see. And we decided to make some groups of material in order to implement all these properties in a faster way in Diana. And for example, we have the properties for the vaults, column, arches, the properties for the main facade, the transept, and the chapels, for the longitudinal walls, and also for the filling of the vaults and of the arches. Okay, but now we have to import all these properties in Diana environment. I think it's very powerful, these tools, because Diana has a lot of material libraries inside already implemented in the graphical interface, and therefore we can go from geometry to material, add material. Here I just showing you one example for the walls, column, and arches. And then, for example, we are going to select the class of element and the material model. For example, here I selected the concrete and masonry, and total strain-based crack model for the material model. And we are going now to apply both linear and nonlinear properties. The linear properties, as already said, were achieved by the sonic test results, and the nonlinear properties were obtained by the mode code 1990 design code. I would like to make you aware that it's possible to also have other aspects to include, such as, for example, the Rayleigh damping. I am underlining Rayleigh damping because later on we are going to use it for the dynamic analysis in the following case study. We can also attach the load in a global or local way, and for example, we can select to attach the global load as self-weight in this way, flagging the load type dead weight. But for example, there are also other possibilities, such as equivalent acceleration, that is the option to perform nonlinear static analysis pushover, that are analysis where the load is applied proportional to the mass along one direction and one orientation, positive or negative. And also we can perform we can define also base excitation loads, and it's a very powerful tool because in this way we can perform a nonlinear dynamic analysis, therefore time history analysis, applying input that the user can decide. And now we can attach the boundary condition from the command supports, and we can do it, for example, per edges, nodes, or faces. I decided to select the option support target type per faces, and I can select all the phases in just one time, and then I flag T1, T2, T3 because I would like to apply totally fixed support. And this is what we can see in the graphical interface. Okay, now we have everything ready to assign all the properties to each element of the whole model. And we can click on this button and select all the elements which belongs, for example, to the class, or a specific class element, a specific material, and we repeat the operation for the whole model. Okay, now everything is ready for meshing the model. It's we have to be careful in this phase because we can have some issues regarding the connection between the elements. The options which Diana gives us for meshing the model are per element size or per division. For example, about Carmo Convent, we selected the option element size and we utilized or dimensions of 20 centimeters or 40 centimeters. It depends on the thickness of the several parts. It's important also to flag this option, adapt element size near curvature, to avoid some mistakes or difficulties in the mesh phases. And it's important to assure at least the presence of 2-3 elements along with the thickness of these of each part of the model in order to have consistent results later on. And then we can click here for meshing all the model. Okay, this is the whole model. In this case, you can see how it is complex and not so easy, and therefore you can also imagine the number of elements, which is really significant. As already said, we set the mesh size more fine for pillars, arches, and the filling, and the other parts of the convent were meshed by sides of 40 centimeters. Okay, in these two slides, I would like to make a kind of summary of what we have done until now, because maybe it can help you to avoid mistakes if you are going to model the complex structure as Carmo Convent is. For example, I suggest you to make the geometry step by step and generating the mesh per parts, not all together, because it's easier to understand if the connections between all the parts of the model are working properly, and if it is working, we can save a backup. Otherwise, we can come back to the geometry definition. It's a trial and errors methodology, but I suggest you to follow this kind of method because it's really powerful and it can save time at the following phases. Then we can set up all the analysis that we are going to see into the detail. But for checking if the model is working properly, I suggest you to run always the linear static analysis and the structural eigenvalue analysis. The linear static analysis is powerful to understand if the units are correct, but also if the total vertical displacement or the reaction at the base of the structure are realistic or not. On the other hand, the structural eigenvalue analysis, also called model analysis, is useful to understand the dynamic behavior of the structure and also for calibrate the model itself. It's very interesting to understand better what is the calibration. Calibrate the model means that we are going to make the model behave realistically as the real structure. So in this phase, we are going to perform several eigenvalue analyses, changing the parameters in order to achieve the frequencies and the mode shapes we obtain from the dynamic identification test. Due to the accessibility of Carmo Convent, that is quite difficult because of the lack of the roof system, we could perform dynamic identification tests just in 2 points of the structure, in the along the longitudinal wall and on the roof of the chapels. And therefore, I suggest you also to take to pay attention on the correct number of eigenfrequencies we are going to select. So, okay, first of all, from the analysis window, you can select structural eigenvalue analysis and then define the number of frequencies you want to ask to Diana. First of all, the more complex the structure is, the more number of eigenfrequencies are needed, because we have to try to stimulate all the parts of the model in order to understand the several dynamic behavior along all the structure. For example, talking about Carmo Convent, that is a ruin, it's a damaged church, this procedure wasn't so easy. And in fact, as you can see, the first modes are always related to the arcade of the arches. We had to see the first mode, which starts to stimulate also the facade and the transept at the 23rd mode. Okay, now we are going to the detail of the nonlinear static analysis, also called pushover analysis. But first of all, I need to make a specification because I'm not going to use the graphical interface because of the dimension of the file. As you can imagine, structures as big as Carmo Convent are really heavy in terms of giga and dimension of the file, and therefore Diana allows us to export the DAT file, which contains all the information about the geometry of the model, and also we can add other kind of loads directly in the DAT file as it is, as we can typing in Word. It's very easy. But it's important to select the proper strings to attach the correct loads and avoid the following problems. For example, the case number 1 is the application of the self-weight, and it is called both in the DAT file but also in the DCF file. The DCF file is the file that contains all the information regarding the application of the loads and also the information regarding the analysis. And you can export directly or say from Diana environment. Talking about the nonlinear static analysis, we have to select the string equiac, as already said before. And the first number in the DAT file recalls the direction in which we are going to apply the load. And the second number is the gravitational acceleration, that in this case positive. So in fact I called this load lateral load positive y direction. And the same way in the DCF file we have the load size we want to apply, but also, for example, the maximum number of iteration and the integration method we are going to use. I suggest you to have the same number of the same kind of outputs, both for the self-weight or for the application of the lateral load. Okay. The selection of the outputs is really important because, as someone said before, less is more, which means that for models that are really heavy, as Carmo Convent is, we need to select the most interesting output in order to save time. And for example, I suggest you to plot the total displacement for creating the capacity curve of the structure, as we are going to see later on. And for example, craft width or tensile principal strength, which are very useful indicator of the deformation which are going to happen while the load is increasing. Other tips that I recommend you are redoing always the mesh if we wanted to change something in the model, and if we have the case of steel rebars inside of the elements, we will have 2 output files at the end of the analysis. And also it's better always to create separate folders between the self-weight and the lateral loads. And one important powerful tool that we have if we want to run analysis in the graphical from the command box is that we can copy the Philos file and in another folder and restart the analysis from the last converging point. And then from the command box, so here you can see how to run the analysis. So we have to select the disk we are going to work, the directory with the command cd and the address of the folder. CD stands for change directory. And then we call with this command Diana-ham plus the name of the DAT file and the name of the DCF file, enter, and we are going to start the analysis. It's very important to select -ham because in this way we are going to say to the command box that we want to follow the analysis while it's running, and it will show the several steps it's going to apply. And in this short video, I show you how to import, once the analysis is finished, the results in the graphical interface. Okay. Concerning Carmo Convent, we performed several pushover analyses, and we obtain different load factor because we utilize this approach. And I'm going to explain you now. The first pushover analysis was made along the y direction, positive, and we noticed that the arcades were collapsing soon. So we decided to create another model and simulating the structure along the x direction negative without considering the arcades. And from this pushover, we noticed that the arcades of this transept were failing. And therefore, the third pushover wasn't with the presence of the arcades of the transept. And then the last one noticed that the main facade started to suffer more regards just the chapters in order to have the behavior just of this part of the structure. Okay, it is possible also to start the pushover analysis from the graphical interface, of course. From this video, you can see how to do it, selecting two kinds of loads, so load steps, one for the self-weight and one for the lateral load. And so if, for example, if you have a smaller model or easier models, it's very useful to use directly the graphical interface. But this, I think that it's quite powerful, but sometimes you cannot restart the analysis from the last converging point. And because of that, I suggest you to try to make an effort and start to utilize directly the command box for running the analysis. So now the video is finishing. For example, here we are selecting the max number of iteration, the convergence norm, the line search options, and for example, we selected the load step for the pushover in the x direction, positive, and the specific sides for the load step decided directly by the graphical interface. And then we can close and run. Okay. So, just for your knowledge, I would like to show you some powerful results we obtained plotting the total displacement and the crack width considering the first pushover analysis along y direction positive. In this, for this analysis, it's really important to plot the capacity curve. Plotting the capacity curve means that we want to represent the inelastic behavior of the structure and represent the lateral load factor versus the displacement, which are expected according to the Diana software. And this is a quite good assumption or method to study the seismic assessment of the buildings, because the lowest load factor corresponds to the most vulnerable part and vice versa. So for plotting the capacity curve, we have to go into this visualization, selecting one point at the top of the structure, and then go in the results window, selecting the displacement in the direction we are applying the load, and with the right click we can go to show table, and then a table of data will appear, and then we can copy and paste the data, for example, in Microsoft Excel for plotting the capacity curve. And so, to conclude our analysis of Carmo Convent, as you can see, the structure is complex, is damaged, is a ruin, and therefore the study is more complicated. But Diana, thanks to Diana, we could perform several structural analyses, more advanced also, and we could understand which parts of the structure were suffering or are suffering more than the others. For example, we noticed that the most vulnerable structural elements seem to be the arcades of the main nave and lateral naves. And then we have the arches of the transept, which present also an high seismic vulnerability. And despite the evident damage that we observe in the main facade, this part of the structure seems stable. And as already said, we obtained the maximum load factor for the last model, which was considering just the part of the chapels, and therefore we can consider this part the safer one among all the parts of the models. Okay, now we can go into the detail of the other case study, which is Loka Haipine Temple, a Buddhist temple, middle sites located in Myanmar. And to create this model, I utilized FX Plus for Diana. In this case, I'm going to show you how to create groin walls and to insert steel rebars inside of the elements with the command embedded solid. And then we will talk about the dynamic analysis, therefore time history analysis. Okay, as you already said, Loka Haipine Temple is located in Myanmar, in the archaeological site of Bagan, which is an archaeological site which contains more than 3,000 Buddhist temples, more or less all dated along the 12th century. And as you can see, this temple is quite particular, especially for Western people, and it contains 3 rooms, which are the porch, the vestibule, and the central shrine. In this case, we have rounded walls, and then we have also groin walls. The dimensions here is more or less 10 meters times 15 meters, and this structure, but also all the Bagan sites, suffered several earthquakes, which brought a lot of damage along the structures. The last one occurred in 2016, and it is called the Chaux earthquake. This is our case study, and as you can see, after Chaux earthquake, the final part of the Sikara, which is this part below the spire, collapsed, and we don't know exactly when. Some reinforcements were added at the corner of the shrine and at the corner of the vestibule, and so this will be an object of our webinar. And from this picture, you can notice that we have original fired clay bricks, but also more modern bricks. As we have done for Carmo Convent, we needed to perform non-destructive tests to achieve the material properties of the structure. So we performed sonic tests to understand the young modulus of the bricks, but also of the reinforced concrete beams. And then we utilize also steel rebar detector to have a kind of idea about the location of the ties and their diameter. The structure is more massive and also more accessible than Carmo Convent, and therefore we could perform more setups. We performed 8 setups along all the terraces of the roof system in Loka Temple, and we achieved the model frequencies and the model shape we wanted to to be implemented later in the calibration phase. Okay, just briefly, I would like to introduce you how to create vaults, growing vaults, and have solid, talking about the geometry, and then I will talk about how to perform from the command box using that file and DCF file the nonlinear dynamic analysis using real earthquake, that is the input of Chalk's earthquake 2016, and also an artificial one. In this case, we start with the creation of the growing vault, importing from AutoCAD environment always the profile of the vault, but also the supports and the internal part of the vault itself. So then we can do extrude of the supports in order to accommodate the vault itself, and then we use the common in order to keep just the real support, the geometry of the real support. And then we can extrude the profile of the vault in one direction and also in the other direction, and we need to fuse the two parts in order to have just one solid, flagging the merge phases. And then we need also to extrude the internal part to be cut from the previous solid we created. So, okay. We do at the end embedded solid. That is not what we are going to explain later on, but it's just a command to assure the connection between the supports and the growing vault. Now, as already anticipated, we are going to explain how to create embedded solid, such as solid element that is the steel that are the steel rebars inside of a concrete beam. We start again from surfaces we made in CAD environment, and then we can extrude them internally, and then after that we can merge the two solids in just one element, and we can change the transparency for seeing the internal steel rebars, and then it's just question of assign material and properties. The concrete is a 3D solid made of concrete, and talking about the reinforcement, we can select a reinforcement from the property manager and then select the reinforcement bar, which contains the information of the material, and also reinforcement bar section to be able to mesh per division the steel rebars. So auto mesh solid and then auto mesh per edge division number 1. Okay. So this is the result of our model made in FX Plus for Diana. We have not only solid elements but also bar elements, and the structure is significantly smaller than before, but the number of elements is really relevant. So I suggest you to select a mesh size range between 0.1 and 0.4. It depends on your cases, of course, but there are also some important options that I suggest you. For example, the definition of the refinement factor, which is possible to find in following this path, and it is a way to increase the size of the mesh where there is no need of having a fine mesh, and vice versa. At the same time, I suggest you to renumber the nodes using the command renumbering, mesh renumber, and then you can select the method of renumbering and do it for the whole model or partial model. This is very useful because in this way you can improve the solution time and save time during the analysis. And this is very important because, for example, just to have an idea, if you want to perform nonlinear time history analysis for this kind of structure, it can take also 1 week. Okay. So, as I already said, we performed the dynamic tests along all the structure, and therefore this phase of the calibration was more detailed. And in fact, we use not only the combination of material properties and the foundation, but also we utilized the MAC model assurance criterion and Douglas Wright method, which considers not only the frequencies but also the mode shapes. What does it mean? It means that we are going to compare mode by mode the experimental displacement and the numerical displacement for all the tested points when we perform dynamic identification test. And therefore, as you can imagine, the model will behave more realistically. Okay, having created the model in FX Plus for Diana environment, we need to export one file more, which is the prenatal file, such as, for example, I call it loca.fxt. And then we can import the fxd file in Diana, and then when it is open, we can re-export again the .dat file. As you already said, when you have the .dat file, it's very important because you can check units, you can check loads, and you can also set new loads. For example, in this case, we are going to maintain the set weight while we are discarding the pushover because we are not going to use it for the moment. And then we are going to select the seismic input. Okay, so from the strings related to the material, we have to add the Rayleigh damping, and as we have seen before, we can do it also from the graphical interface, and these two numbers represent the damping properties, which depends on the frequencies you are going to select as a representative for the seismic behavior of your structure. And then we can talk about the base excitation load. Base excitation is the option we have found before in the graphical interface to apply dynamic inputs to the structure. The first number, the first string refers to the load we want to apply, such as base excitation. The first number is the direction along which we want to apply the seismic input, and then the second number, that is 1 in this case, is the amplification factor we want to apply. In this case, it's 1 because we want to apply the real earthquake, such as chalk earthquake. Then this information below regard to the input we are going to apply in the 3 direction, north-south, which stands for X, east-west stands for Y, and vertical for Z. This 30 means 30 seconds, and 0.01 is the time step. Okay, then we have also to take the DCF file to run the analysis, and I suggest you to ask not only for the normal result but also for the scan result. Have the scan result means that we are going to sum all the information of each time step until the end of the analysis. And I suggest you also to put one number here in brackets, which means that we are going to save just a limited number of data, of steps, in order to avoid very heavy data. Again, just for having an idea, at the end of a dynamic analysis, you can have also 60 or 70 giga, more or less. And this is the input we are going to apply. On the left side is the real earthquake, which the PGS is not so high. Actually, this earthquake is not so strong, also because the distance from the epicenter is 35 kilometers, and then we decided to amplify it, changing the amplification factor in the DAT file, in the DCF file. In the DAT file for having an input similar to the spectrum which is designed for Bagan site. And we ask also for an input which is artificial, and this is fitting the design spectrum expected for the center of Myanmar. The results are shown in terms of displacement and total principal strain, because I consider them as a good indicator of the deformation along the structure, and also because of the time and because of the heaviness of the data, we couldn't ask for more outputs. And as you can see, the level of strains is not so relevant, but once we are going to amplify the seismic input, the indicator is increasing significantly, and especially considering the artificial earthquake. At the end, to be more complete, to suggest to local institution a kind of new strengthening proposal, maybe for substituting the reinforced concrete beam, we suggested to use steel ties modeled in FX plus for Diana as embedded solid, as I showed you before. And we perform an iterative process changing the position of the ties and the diameter, and it's really easy and fast to change the diameter from the DAT file, because it's just a question of changing the cross-section in the steel for the steel material. And then it's worth to underline that for sure, talking about an historical monument, we had to design this new strengthening proposal considering aesthetical details and the original shape of the structure. And because of question of time, because I had to deliver my thesis, I could just perform pushover analysis that are quite faster than dynamic analysis. And so, as we did for Carmo Convent, we can do a comparison between the unstrengthened configuration, which is below, and the strengthened configuration with the steel ties. As you can see from the capacity curve, the behavior is increasing, almost of double, and the damage also, the strain, is representing a more widespread deformations along the structure, and less evident, especially the out of plane of this eastern wall. Okay, now we can conclude as I hope you understand the complexity of the structures, but also the high level of performances that Diana is giving us in terms of advanced analysis, but also in terms of graphical interface and compatibility between several other software. And for sure, the pros are much more than the cons. The cons are just related to the dimension of the file, I think, and it's really, really important to understand the tools that Diana can give us, for understanding the structural assessment of this structure, even if these case studies are monumental, complicated, and very damaged. So here I show you some references that I utilized from the historical part till the modeling and the calibration, the material properties, and the seismic input we utilized. And if you have any information or questions, please don't hesitate to contact me or also my colleagues. And thank you for being here again.